This board, we start the famous halting problem, Turing's halting problem, probably the most famous result not only in this course but in the whole of the theory of computation. It's that big. So when the moment arrives, I will give a trumpet fanfare in my style. Now, now that we're close to it, and we'll get more into it next board, but we'll start the process in the very end of the third session, and then more into its implications a bit in the fourth session. But the next board we'll get into the actual theorems about it. So we won't get into the nitty-gritty of it this board. But it makes me reflect. Since I have a kind of lateral mind, I push the stack many times, and then I have to remember how to pop it in the appropriate order. Now, for example, this weekend I will be a keynote speaker at a fairly sizable international conference in China with two of the top universities in China. And one of the things I'll be trying to do is to appeal to the big names in Chinese artificial intelligence, because that's what the conference is about. And I will try to persuade them to persuade in turn the Chinese government to invest heavily in artificial brain technology, because there have been recent breakthroughs. Brain scanning has now reached the point in terms of resolution both in space and in time. So in time, quickly enough to see the individual firings of single neurons. So spatially, the resolution is fine enough to actually see the neurons, and time-wise, the resolution is fine enough to see the actual firing. So that means we increasingly brain scanning technology will be able to just trace out the history of the firings of neurons, which is just absolutely amazing if you think about it. And the other thing is, the past year or so, our supercomputers have surpassed the estimated bit processing rate, the bit flip switching rate of the human brain, which is estimated at about 10 to the power 16 bit flips equivalent information processing, bit flips per second. And you put those two together, so that we can expect in the next few years an explosion in knowledge of neuroscience. Now that we have these powerful new tools, finally we've got the tools. We can actually look at the brain in action at synaptic level. And the Germans recently announced that using electron microscope techniques, the latest machines, that they will now create a full anatomy at synaptic level. In other words, all the neurons and all their connections of a rat brain, which is about 1,000 times smaller than the human brain. So that's still a huge number of, well, let's see, we have the human brain has 10 to the 11, it's 100 billion neurons. So divide that by 3, so it's 100 million neurons. And then you multiply that by, 10 to the 4 or so to get the number of connections, in other words, synapses. Anyway, so this, in a few years with this German project, we'll have a full anatomy of the rat brain. We'll be able to simulate, put that into our super duper computers. Anyway, so this weekend, I'll be talking about all these latest developments, and eventually I'll get into the politics and say that this the development of artificial intelligence is such that sooner or later humanity is going to have to decide whether we build these artificial intellects, these godlike, massively intelligent machines, thinking a million times faster than we do, virtually unlimited memory. They will have an intelligence theory. They'll understand what intelligence is and how to increase it, so they can then apply those lessons to themselves. This sort of thing. So in the short term, the next few decades, I'll be advocating that the Chinese government invests heavily in artificial brain research and development, because artificial brain-based products will create the world's richest industry within a decade. I'm betting. So all major countries, tech-based countries, Europe, America, Japan, Korea, India increasingly, and so on. These countries will have to invest heavily, China, invest heavily in artificial brains research. Now, why am I talking about all this in relation to this course? Well, it's yet another arrow, if you like, a pointer towards the idea that computers are just absolutely godlike, incredibly powerful. And so it's sobering to learn that no matter how powerful they get, there will be tasks they cannot do. Now, it's a very valuable and sobering philosophical lesson to be learned. And this board and the next, and then next chapter, particularly next chapter, chapter 5, we will give lots of examples of problems that are just unsolvable. Right? So, provably unsolvable. Which let those two terms sink in, because it sounds like an oxymoron, like a self-contradiction. Provably unsolvable. Right? I mean, what a concept. And yet, we're going to do it. We'll start. We'll start on it. This board, and next board we'll actually do our first famous example of something that is provably unsolvable. And then next chapter we'll give lots of examples of things that are provably unsolvable, and we'll build up an expertise, techniques on how to prove that certain things are unsolvable, which is quite amazing. And it's one of, for me, what's about to come is the absolute highlight, and not just me, lots of theorists who love this kind of stuff. It's just amazing. For example, to consider an analogous situation, I've not yet, I expect to, but I've not yet had the experience myself, but I've read that quite a few mathematical logicians, when they really get into Gödel's theorem, the incompleteness theorems, well, it's usually the second one is referred to as the Gödel theorem. It's the main one. When they realise that when it hits home emotionally, when the full impact of Gödel's theorem, showing that well, I won't go into it. I've talked a bit about it before, but when the penny really drops and they finally get it, it clicks, the full impact of the theorem in their mind as they're studying it. It's for them a kind of almost religious experience. It's a deep, emotionally shocking, traumatic, enlightening, awe-inspiring, jaw-dropping experience. So, I'm hoping to have that. Now, I get a sort of mini dose of that already with what we're about to do, this board and the next chapter, and I hope you will too. But this notion that no matter how powerful and godlike our computers become in the future, and I see the rise of the intellect this century as the dominating theme of our century, of our historical era, because what's at stake? Well, the survival of the human species, no less. So, a big deal. But same bit before. There are limits. Even an intellect, presumably, would not be able to solve certain problems because they are provably unsolvable. Sobering. Right? It's food for thought. I know also Gödel, because I've got his biographies, was fascinated by the question, to what extent is the human brain a machine, and hence subject to his own incompleteness theorem. There's been a lot of debate on that, and that whole literature is something I really want to get into. And of course, if I really want to learn something, the best way to do that, and that's the whole point of all this MPC stuff, is to teach it. So expect in the future I will be giving courses on the relevance or otherwise of Gödel's theorem to the human mind. Fascinating question. Is the human mind more than just a Turing machine? Can it do more? Is it sort of super Turing? Open question and fascinating. All right, back to the nitty-gritty. We are this couple of sessions. We'll finish off a few proofs, theorems that certain languages are decidable, and hence, proving that certain languages are decidable. That allows you to solve certain computational type problems. Remember, consistently we've been translating computational type problems into their equivalent. Is a particular string a member or not a member of a particular language? And if it is or isn't, then you get a decision, yes or no, whether a certain computational problem can be solved or not. Right? Well, talked about that at length, so I won't go into that yet again. Okay, so we've got 1, 2. Only 2 theorems on this board. All right. So here's the first one. Now we're in the context now of grammars, context-free grammars, and we want to know: is it possible? We